Welcome to this explainer. Today, we're diving deep into the high-stakes, sometimes overwhelming world of modern AI and machine learning engineering interviews. The tech hiring landscape, it's completely transformed over the last couple of years. If you want a seat at the table building the next generation of foundation models or these massive agentic systems, you need a very specific, highly specialized edge. And that is exactly what we're going to build for you today. Let's get right into it. Here's the brutal reality. If you're stepping into a technical interview at a top-tier AI lab today, those classic software engineering and basic algorithm questions, they just aren't going to cut it anymore. When an interviewer slides a question like, could you optimize our LLM's memory footprint across the table? They absolutely do not want a textbook definition. They want to know if you have the practical, under-the-hood knowledge to solve real, incredibly expensive scaling bottlenecks. They're testing if you understand the actual architecture driving the industry right now. So here is our roadmap for the 5 major rounds of the modern AI interview. We'll hit core LLM architectures, move into alignment and fine-tuning, tackle RAG and agentic systems, dive into MLOps and system engineering, and finally wrap up with classic machine learning. Let's kick things off with round 1, core LLM architectures. This is all about understanding the foundational math of modern AI. A classic interview opener is asking you to break down the fundamental difference between encoder, decoder, and decoder-only models. What you really want to do here is illustrate exactly why decoder-only architectures like Llama 3 and GPT-4 totally dominate the space. You'll want to casually explain to your interviewer that causal, unidirectional attention scales way better during pre-training. Plus, make sure you highlight that it simplifies autoregressive caching and perfectly leverages next token prediction across both instruction and generation tasks. Boom, that's the practical engineering answer they're digging for. Now, when an interviewer brings up rotary position embeddings, or ROPE, sure, they know it efficiently encodes relative positional information, but here's their hidden motive. They're actually checking if you know how to smoothly extend a model's context window. So you'll want to casually mention that ROPE allows for context extension using frequency scaling techniques, like YARN. Dropping that little nugget shows you understand how the underlying math translates directly to unlocking massive input prompts for real-world users.
And inevitably, the optimization question is going to come up. Flash attention computes exact attention by completely bypassing the dreadful I/O memory bandwidth bottleneck between slow high-bandwidth memory and fast SRAM. And it does this leveraging a clever little trick called an online softmax trick. The crucial takeaway here, when they ask about flash attention, they aren't just testing your math skills. No, they want to see if you understand the hardware. They want to know you can save the company literally millions in GPU compute costs without ever having to approximate the data.
Moving right along to round 2, alignment and fine-tuning. This is where we talk about teaching foundation models to actually behave and follow instructions. Interviewers absolutely love comparison questions, and knowing the difference between PPO and DPO is going to score you major points. Look, PPO is heavy. It's this complex online reinforcement learning loop that requires running 4 concurrent models at the exact same time. It's a lot. DPO, on the other hand, mathematically parameterizes the policy loss directly over preference data. By explaining that DPO turns preference alignment into a stable, completely offline binary classification task without needing those extra critic and reward models, you're proving you know how to vastly simplify the engineering pipeline. So, what does the number 99 mean to you? In this context, it represents the percentage of trainable parameters you can literally eliminate using LoRA, or low-rank adaptation. When the interviewer asks how you'd fine-tune a massive model on a tight budget, you just explain that by freezing the base weights and injecting these tiny, trainable low-rank decomposition matrices, you can drop the parameter count by 99% or even more. This is basically the ultimate proof that you know how to be highly parameter efficient.
All right, let's jump into round 3, RAG and agentic systems. This is all about connecting large language models to external tools and real-world data. They're almost certainly going to ask you to compare sparse retrieval, which relies on exact keyword matching, with dense retrieval, which uses embeddings to capture deeper semantic meaning. But here's the trick, the real curveball. They want to know how you'd combine them. The absolute golden interview answer here is hybrid search using reciprocal rank fusion. You just calmly explain that reciprocal rank fusion perfectly balances keyword precision with semantic depth by merging their rank lists. And the best part, it beautifully does this without needing any messy score normalization. Moving from simple retrieval over to true autonomy, you really need a solid grip on agentic workflows. To completely demystify this for your interviewer, bring up the React prompting pattern. You can frame it kind of like human problem solving broken down into an iterative loop. First, the model generates a thought about its current state.
Then it takes an action by calling a specific tool. Finally, it receives an observation from that tool to inform its very next loop. It's incredibly important to mention that this specific pattern prevents those frustrating deterministic dead ends and allows the model to dynamically self-correct on the fly. Next up is round 4, MLOps and system engineering. Get ready because this is about the brutal reality of scaling, serving, and actually deploying AI models.
Okay, we really need to dive into this one because distributed training is a massive topic. If they ask how to train a model that's way larger than a single GPU's memory, you immediately bring up zero. Zero optimization is basically like dividing up a giant complex jigsaw puzzle across multiple GPUs. Stage 1 shards out the optimizer states. Stage 2 adds the gradients. And then stage 3 goes all out. It shards the optimizer states, the gradients, and the model parameters themselves across all the GPUs. Hitting these points proves you know exactly how to train trillion-parameter behemoths without constantly running out of memory.
You'll definitely want to commit these details to memory. Hardware precision trade-offs are an absolute favorite topic for interviewers. So FP16, it requires loss scaling because it's super prone to dynamic range underflow. Then you have BF16, which is the modern gold standard because it conveniently keeps the exact same dynamic range as a standard 32-bit float. And finally, FP8 is the exciting new frontier for efficiency. Showing you understand these specific bit-level details proves you know how to balance massive memory savings against catastrophic, career-ruining training failures.
Here's another major gotcha to watch out for in the MLOps round: managing the KV cache. It stores past token matrices to dramatically speed up text generation. But the memory footprint, it's absolutely huge. You have to show the interviewer that you know continuous, iteration-level batching, and page detention are strictly required to manage this massive KV cache footprint. Because without them, you're going to end up with severe memory fragmentation and totally unacceptable GPU idle time during serving. And nobody wants that.
And that brings us to our final hurdle, round 5, classic machine learning. These are the foundational theories that literally never go out of style. A fantastic question they love to ask here is testing your ability to explain the difference between data drift and concept drift. The absolutely crucial point is distinguishing between the two using a clear, real-world example. You can explain that an audience demographic slowly shifting over time, well, that's just data drift. But say a sudden global event completely alters consumer purchasing behavior overnight, that is concept drift, because the actual underlying relationship between your features and your target labels has fundamentally changed. You absolutely need to know your normalizations inside and out. Batch norm is typically for vision, and layer norm is for your standard sequences. But when the interviewer inevitably asks why modern LLMs specifically prefer RMS norm, you can confidently tell them that RMS norm assumes a zero mean and scales inputs using only the root mean square. Simply dropping that mean calculation saves a massive amount of computational overhead. We're talking between 10 and 50% per layer, and it does all of that without sacrificing a single drop of accuracy. To wrap up the technical grilling, they might hit you with the classic exploding or vanishing gradient problem. By rapidly firing off these standard mitigations, residual connections, layer normalization and RMS norm, ReLU activations, gradient clipping, and specialized weight initializations like He or Xavier, you're demonstrating a really deep foundational understanding. It shows you completely grasp how gradients multiply sequentially via the chain rule during backpropagation. Ultimately, it proves you understand the actual mechanics of how a model learns. Ultimately, mastering the concepts we've covered in this explainer is what's going to get you the job today. It arms you with the exact technical depth and practical intuition that interviewers at top AI labs are desperately searching for right now. But honestly, looking at all these automated optimizations and autonomous agents, it kind of leaves us wondering something bigger. As these agentic workflows become truly autonomous, how long until the correct answers to these brutal technical questions are written and even implemented by the models themselves? Think about that as you prep for your next interview. Thanks so much for joining me on this explainer, and good luck out there.